Okay, hello everyone. Let's start our lecture. So I realized that the material for today's lecture was a bit too maybe heavy. There was a lot of computations, and actually it might look as if it arrived without a conclusion. That's why today I also want to give you an example of how to use all these ingredients which you probably have seen in the pre-recorded lecture in order to get to a meaningful result in the quantum electrodynamics. But before that, I would like to address the question, to finish the discussion which we had in the previous lecture and didn't have the chance to converge on this. And another point is that I again received very interesting questions from you. And I must say that these questions require quite some discussion. Therefore, I decided that what I will do, I will prepare the slides with the answers to these questions, and then I will share them with you. But I will not spend time right now going through the responses. I hope it's okay. You don't mind? Because otherwise we will not have time to go through everything else which has been prepared for the lecture. Okay, so what we'll start with, we'll start with the discussion which we haven't finished last week. I'll share with you the slides at which we have stopped. Here they are. So here you can see the slide which we did have a chance to discuss. And again, in order to achieve some sort of interactiveness from you, I would like you to log into the same website as previously, and I will scroll forward to the question at which we stopped. Let me start the questionnaire, and then share with you the ID because it's automatically created. So here's the ID. So you go to this website and you enter this ID there. And then I want to go directly to the question at which we stopped. Okay, here it is. So before that, so here's again the slide at which we are looking. This is a measured spectrum of dimuons with the LHCb detector. So basically in each event, we are looking for a pair of muons of opposite charge and then compute the invariant mass. And here how it looks like. And as you can see that in principle spectrum is more or less flat with several peaks being here like eta meson, then this one corresponds to rho and omega, this one corresponds to phi, and the leftover tail here is referred to as high mass dimuon, though in principle it's not very high mass, it's like 1 GeV and above. And the question is why particles look like a peak in an invariant mass spectrum. So do you want to, does anyone want to answer to this? Any ideas? Okay, and then the question is why some peaks are wider and some are more narrow. For this, I'll ask you to go to this, to try to do the exercise, which is on the interactive session. And the first question is, what is rho zero particle width in MEV? Of course, probably you don't know by heart what is the width is, and what you should be able to do is to go to this website. I paste link in the chat again. find the property of, find this particle, find its width, and paste it as an answer. Does it work for you? Since I don't see any responses yet coming in. One. Okay. So maybe I can help you. So you go to this website and there you have PDG Live interactive listings. Go inside, and then this meson should be in the light unflavored mesons. There you should be able to see rows 770. And then find the neutral row, 770. There are several values, but they are not much different. Just what matters is the order of magnitude. Okay, 3 people managed to find it. Do you need some more help? Do you need me to guide you through the sharing at the of my browser? You can answer in chat if you cannot answer by voice. Okay, 4 responses out of 15. So, okay, it is there in chat. Okay. PDF document is also fine. And just so you can do like this. I prefer usually using interactive one. So there you can see mesons, then light and flavored mesons. And there you can find raw. And then what is we interested in is the width of the particle. And if you might remember also from the first lecture is that width is usually also is denoted by the Greek letter gamma, and it's inversely proportional to the lifetime of the particle. But here you can see directly width in MEV, which is written in the PDG. And you need to enter this number into this question as an answer. So I'm still waiting for everyone because it's a basic skill to be able to navigate over PDG, and I would like to make sure that all of you can do it. Okay, so still it's 8 out of 16 people who are logged in. So do you need some help? 9. Okay, so it takes some time. Now what I will do, I will just split you randomly in groups so that I hope that in a group there will be at least one person who managed to do it, and they will explain to another person who doesn't know how to do it, how to actually do it. Just stop share for a moment. Okay. So now you can all go to your own breakout rooms where you split in small groups and where you can have a discussion among yourselves how to finalize this task. I hope that people who did not join are those who know who already answered, basically. Yes. Okay. Did the discussion help?
A little bit.
But I still see that not everyone has answered. I see 9 answers out of 15. Typically, of course, I would not wait for 100% answer, but this is a very a straightforward task which just shows how you can click on the links and read the numbers. And I really expect that everyone is able to do it. So unless you don't have, I don't know, all of you have internet connections since all of you participating in the Zoom.
Am I correct that they should send an answer on website, view the website, or they should send answer due Zoom chat?
So the answer should be inputted in the website, which you all have entered. This responsewhere.eu, right? You entered there and you see the question now.
Because because if I try to write something in the participant ETK, I cannot write something.
Why?
I don't know. I try to write, but it doesn't work. Maybe other people have
similar issues.
This similar problem. I don't know.
Hmm.
You mean the chat under the question?
So let me enter the room, join the session. So there is a question. Let me share this browser window.
I suppose everything all right. I write down the answer and it said that your response has been submitted. That's why I think that everything all right.
Yes, everything's fine. So you see, but I see that 16 people are connected and 11 answered. So one of them is myself. So I go to the website and I see some numbers. They are a bit different because there is experimental uncertainty. I put just some number. It doesn't matter. All of them are correct. What matters is the order of magnitude. So I put 150 and I send this answer. Your response has been submitted, right? So now 12 people out of 16 have answered. So 4 still didn't do. And as I understand, at least for one of you, you just cannot write there anything, right? Okay, so I stop this and I hope that in the next question, which is similar, it will be faster because we cannot spend really 20 minutes on such thing. So now I show results and we can see that most of the people got the answer correct. They picked some number out of the range which is available here, row 770 bits, which is of the order of 150 MeV. And then a few more people got confused. So one of them inputted the mass, 775. So it's a number on the top. So it's raw mass. But the question was about the width. So the numbers should have been one of these two, these ones. And one person inputted 363, but this I'm not sure where it comes from. So it's not here. In any case, the width should have been 150. And here it's an interesting thing to compare this number 150 with the actual mass, 770. So let me share again the spectrum. And you can see here that indeed rho or omega, so these are two particles with close mass, and rho is at about 770. It's rather wide particle, that's why it looks so wide. Now, the next question for you to understand how it can be different is about the eta particle. Now I again understand that it can be a bit ambiguous, which eta particle. That's why I will give you a bit more precision. So you should take the lightest eta particle, which has a mass, well, the first eta which you see there without any primes or whatever. And again, input there the width of eta particle in MeV. Please do it. So eta is here. Here it is. Okay. Okay, we have 9 people who answered. I will proceed. So this time responses are a bit wilder, a bit different range. Again, if you go to ETA, let me stop share and share with you the screen. This one. So we can find ETA width is 1.31 keV. So in MEV, it indeed should have been 0.00131. So this answer is correct. Now we have a bit some more answers. This one certainly is wrong, is just in keV instead of MEV. This one is wrong translation from keV to MEV. Then the others, I'm not sure where they come from. But in any case, just for you to understand what is being asked for, if you go to the description of the ETA particle, here, I paste the link in the chat so that everyone can go there as well if they didn't find it yet. And you can see here the first 2 lines. First is ETA mass, 547 MeV, and second is ETA width, 1.31 keV. So you can see that ETA is indeed much more narrow than the rho. And this is also something which you can see in the plot in this spectrum. But this still doesn't answer the question, doesn't fully answer the question posed in this slide. So here is the answer for you. Basically, the observed resonance shape is formed by 2 effects. First effect is the one which we are looking into right now, is the particle decay width gamma, which is equal to 1 over lifetime of a particle. And the shape of a resonance is governed by the relativistic Breit-Wigner distribution. So basically, here's the shape of the peak, which you see in the spectrum. Then the larger the gamma is, the wider would be the resonance in principle. Then the other important effect is the detector resolution. So if you remember from the previous lecture, the mass peak, the invariant mass shape, is computed using momentum energy measurement from the detector, and then Gaussian uncertainties in this measurement would translate into the Gaussian widening of a mass peak. And then the final form of a peak which you observe is a convolution of the 2 effects, typically with one of them dominating. So if you look at the, for example, particle rho, for sure, this one would dominate by the natural width of the rho peak because, well, it's 150 GeV, so it's really much larger than the detector resolution itself. Well, for ETA, the natural width is 1 keV, and here the width is certainly more than that, and here it's fully dominated by the measurements effects. Here's how the spectrum looks for larger energy range. So this time it comes from the CMS detector, and the mass goes as high as 200 GeV. So in this case, you can also see a Z here. And then we have the next question is, what is Z width in MEV? Z boson width, this particle. You again can answer in the browser by checking the number in the PDG. In this case, you need to look for Z boson. And Z boson is found on the gauge and Higgs bosons. So it's a gauge boson. Okay, very well. Now you are answering much faster than before. So I get it that you will take a hold of this website, which is very nice. Let me stop share so that I share another window. Okay. So I have 12 responses. I stop it and show results. You can see. So now we found it. Okay, and there is again some confusion in the units because ZVITS is reported in GeV. It's about 2.5 GeV, and the question is in MeV should be 2,500. So this time it's very good. The last one I don't really understand where it comes from. There is no such number. Okay, anyway, so you can see that the width is 2,500 GeV. And again, let me stop share and share back the spectrum. So here you can see basically that for Z-peak, the natural widths and detector effects are comparable, let's say, and that you can have contribution from both when you try to compute it. Now let me see quickly what we have here. Okay, so now here's another example of the spectrum. You can see the spectrum again of dimuons, which split basically here in this spectrum. It's measured by the Alice detector. And here you can see the contribution of the various resonances. And now I will not do a poll. I will just ask you yourself, since probably you already remember some of these values, we will just now looking at them. What are the masses of the particles shown in the plot? For example, rho, eta, omega, and phi. So for rho, you remember it was 770, somewhere here. And here is the contribution of rho to mu is shown with this black line. Then, for example, phi mass is 1020, and here its contribution shown with the magenta. And also there is, you can see the contribution for eta goes to mu is available here, and some contribution from eta is available here. So now my question is, why the peaks do not always correspond to a particle mass? Do you have any ideas in this plot? If you remember the eta mass, was about 550 GeV, and we have the peak from eta here, and we have much larger peak from eta here. Now this peak is not centered at 550 GeV. Why is that? You can answer in microphone or in chat. Yes, so we have another particle in the decay. So in this huge peak, we have eta decay into mu gamma, and the invariant mass is computed only with 2 muons. So gamma is not taken into account. Basically, one particle is lost, and what we see in this peak is not the actual eta mass, but the invariant mass of only 2 muons out of 3 particles to which it's decayed. And this also is kind of correct for other partial reconstruction decay. So you have, for example, here omega going to mu pi 0, and if you reconstruct only 2 muons out of this decay, you get this shape instead of this nice peak of omega going to mu. So here's for you another source of background, which is seen in various physics analysis, which comes from the partial reconstruction of the case. Now, another question is, why in this spectrum there is no entries below about 200 MeV? So you see, it goes down to 0. There is no data entries. So this data point is the last one which is present. Any ideas? You can answer in the chat or by voice. So the plot shows invariant mass computed of two muons, mu plus, mu minus. And this mass is always greater than about 0.2 GeV. Why? Now, do you remember what is the invariant mass of the muon itself? If you don't remember, you can check in PDG and answer in the chat or by voice. Yes, so mass of the muon is about 100 MeV, 105 or something like that. And of course, the invariant mass of the computed out of two muons cannot be smaller than sum of the two masses of the muons. Therefore, such an invariant mass spectrum has an endpoint at two muons mass. So, and this would be the case for any invariant mass plot which you see. So for example, you can have some more complicated analysis, having more particles in there, having some intermediate resonances, and it will have this feature that it cannot go below the sum of the rest masses of the participating particles. Now let's go a bit to the Cherenkov radiation. And here in this plot, you can see the plot obtained with the LHCb detector, rich detector at LHCb. And it shows for different particles the Cherenkov angle in radians as a function of particle momentum. And we see distinct populations for different types of particles, like protons, kaons, pions, muons. So the question is, why all the curves here have an endpoint? And this is also related to the material which was shown in the lecture, in the previous lecture. And actually, to help you to answer this, you can calculate a small task, again, in the browser. What is the minimal momentum for a muon in GeV to produce Cherenkov light in LHCb rich? But it doesn't have all the information. Here it is. Okay. Okay, so the answer why all the curves have an endpoint. So do you remember the condition when a particle can produce a Cherenkov light? In the medium.
When its speed is higher than the speed of light in the medium.
Yes. So basically, it should have high enough speed or high enough momentum in order to produce Cherenkov light. So when the particle is rather slow, has low momentum, then it stops producing light, and therefore, if you go very low in the momentum, you don't have any more entries for a given particle. So here for you, the material from which you can compute the answer to this question: what is the minimal momentum for muon in GeV to produce Cherenkov light? For this, you need to know refractive index of the material. It's equal to 1.0014. And by using this number and material from the previous lecture, you should be able to find an answer to this question. Let me maybe open the needed slide from the previous lecture to remind you. So let me paste information in the chat.
Can I ask a question about material?
Yes.
Am I right that that material is aerogel or something? Something
Yeah.
that
Yes.
is it aerogel? Yeah.
Yes. Yes.
Yes. Yes.
So here's basically what you need to know is the refractive index for this material and the relation between the Cherenkov angle and momentum. Yes. Stop share. Here it is. So light is emitted if this condition works, or MC smaller than P square root n squared minus n. So from here you can compute maximal or minimal P with which the light is emitted. Can you please do it for muon and paste an answer here? By the way, you can easily check your answer. So stop share by looking back at the plot from LHCb which I was showing you previously. So it's clear that you can read out the number from the plot. And just with computation, you can get it more precisely. Okay, I see that 4 people already computed, pasted their answer. Okay, let me share then the answers with you. Here it is. Okay, 8 people have answered. Just. Okay, so the answer should have been about 2 GeV. So the last 3 answers are the most correct ones. And the previous ones, I'm not sure what kind of, how they were obtained. But in principle, you just should take the mass of the muon, which is 100 MeV, and divide by square root of n squared minus 1. And from there, you get the minimal momentum for a muon to produce Cherenkov lights. So if you get muon softer than 2 GeV, then it will not leave any signal in the LHCb reach. Now, few more small things to discuss about the detection is here. So in case if we conduct momentum measurement in the detector, we of course have some precision of this momentum measurement. And the total resolution, which is achieved with the detector, combines two effects. First has spatial resolution component, where basically relative resolution, sigma p over p, so uncertainty on the momentum divided by the momentum itself, is proportional to the momentum. So here is this line. On this graph, you can see this graph is composed of 2 axes. On x-axis, we have momentum of the particle. On the y-axis, relative momentum resolution. So it's this one. And then the second component is multiple scattering component, which actually has a relative resolution more or less constant, so this one. And then total uncertainty is just the addition of the two. So basically, that's why the total momentum resolution in any detector would have shape like this. You will hear about this in more details when you will discuss the momentum measurement in the next lectures. And here for you, some example of the muon momentum measurement done in CMS. So you can see in this plot 3 curves. Green curve, this one, corresponds to the muon momentum measurement precision when measurement is done only with muon chambers. So here's the transverse slice of the detector. We have collision point here. Then this is tracker, calorimeters, coil of the magnet, and here come muon stations. Muon flies in the magnetic field like this. Why it changes the trajectory? Because B field changes its direction. So inside magnet, it goes in one direction, and then outside it goes in the opposite direction. That's why muon changes its curvature. And then you can measure the momentum of the muon by using only the information here. And here's the resolution which you get. And blue curve corresponds to the resolution which you get by measuring muon momentum only with the tracker. So by looking only at this piece of the tracker. And you can see that these two curves look very much different between each other. So the question is why? Here I will just give you an answer. So in case if you have used muon chambers only, you can see that this flat component, and flat component comes from where? From multiple scattering. It's really huge. So that's because before entering the muon station, the muon passes through a lot of material here calorimeters, the coil of the magnet, and then inside the muon stations as well, it goes through the return coil of the yoke of the magnet. So these gray blobs are basically a lot of iron. And that's why the multiple scattering of the muon interaction with the matter is large, and this multiple scattering matters a lot. That's why it's so large. Well, in the tracker, you don't have much material. That's why multiple scattering component is basically negligible. Then also, if you look at the spatial component, it's also better in the tracker only, just because tracker has much better spatial resolution. So there it's like tens of microns, while in the muon chambers, it can reach centimeters. And then all gives you the combination of the measurement of the two subsystems. Now, another example of the precision of the detectors is the energy measurement at the resolution. So for energy measurement, the picture looks different. And if you look again at the relative uncertainty of the energy measurement, so sigma E over E as the function of the energy, you see that here the measurement improves with the energy. And usually the resolution of a calorimeter has also three components: stochastic, noise, and constant terms, which again you will hear about in more detail later on. Just overall, basically, you should see that the higher the energy is, the better the resolution of the energy you get. And you are basically dominated by this component over there. Now the question is, the conclusion of this discussion, that if we go to higher energy particles, so we rise particles momenta and energy, and we see that momentum resolution would degrade and energy resolution would improve. So the question is, can we always combine momentum and energy measurements to achieve the best result? And here for this, you can think about this question while answering another questionnaire with multiple choice. So for which particles you can combine energy and momentum measurements to maximize the precision? Okay. So we have 9 responses out of 16. Let us discuss the responses. Okay, so here you should be able to see all of the responses which you submitted. And by green check marks are the responses which are supposed to be correct ones. Others which are not correct. So first of all, we can combine energy and momentum measurements only for particles for which we can have both energy and momentum measurements. We should remember that momenta we can measure only for charged particles. So for neutral particles, we do not have momentum measurement. That's why neutral particles like photons, see, cannot be an answer there. We do not measure their momentum. Neutrinos, we do not see in the detector at all. So for this, we also cannot combine anything since we do not measure them. And for neutral hadrons, we also cannot measure momentum. That's why neutral hadrons cannot be there. Then the charged particles which remain are electron, positrons, muons, and charged hadrons. So the question is whether we measure energy for these particles. Yeah, there is something in the chat. Yes, you can measure momentum also by looking at the time of flight, but it's also only for charged particles, not for neutrals. Since only charge for, we measure time of flight also only for charged particles. Okay, so energy. So for muons, we cannot measure energy since we would need to have a very thick calorimeter in order to absorb all the energy. That's why we do not have energy measurement for muons, we have only momentum measurement. And therefore, we can measure the energy only for electrons and positrons in calorimeter and for hadrons in hadronic calorimeter. That's why the answer should have been A, B, and E. And just to show you how it looks like in the actual detector, I share with you the last slide. This one. It shows how combining energy and momentum measurement for electrons and positrons looks like in CMS. So here you can see the plot. It shows the energy of the electrons between 10 and 100 GeV. Here is the resolution in percent. And then basically green points correspond to the precision which can be obtained by the tracker by measuring the momentum of the electrons. Then red points are obtained by using only calorimeter, by using only energy, and blue points from combination of the two. So basically for lower energy electrons below about 30 GeV, it really helps to add tracking information, while for more energetic electrons, the measurement obtained with the calorimeter would dominate the picture. Okay, I hope that with this discussion, particle detectors came a bit closer to all of you. And now I would like to use remaining half an hour just to go through the example of a calculation which we could do by using the information which you should have obtained by looking at the pre-recorded lectures. Do you have any questions on the exercise which we did up to now? Seems not. Okay. So here in these slides, I wanted to give you an example of quantum electrodynamic calculation, which uses as an input all the steps which we have seen in the previous 3 parts of the lecture prepared for this lecture. So for example, if you want to look a QED process, calculate the QED process, plus and minus going to mu plus mu minus, here are the steps which we need to do. First of all, we need to draw all possible Feynman diagrams. And in case of the process where you have E plus E minus going to mu plus mu minus, there is only one lowest order diagram like this in QED. Of course, if you consider also weak interaction, you can have an exchange via Z boson here. So that's why additional diagram appears. But in this case, in QED, there is only one diagram with the photon, and the amplitude m should be proportional to the charge of the electron squared, because we have 2 vertices, each of them contributing with the factor of E, and therefore total amplitude is proportional to alpha electromagnetic. Then we can have many second order diagrams, for example, when the photon in between also splits into a loop of fermions, and we can have like electrons or muons or quarks running in here. Or for example, you can have a photon running between two final state muons and all the other diagrams. But in this case, we add two more vertices. So it means we add another factor of E squared, and overall amplitude starts to become proportional to alpha electromagnetic squared. Then in principle, for each diagram, we would need to calculate the matrix element using Feynman rules, which again were outlined in the lecture. Then sum the individual matrix elements, means sum the amplitudes. And here you should remember that since we are summing amplitudes, we can get the interference of the diagrams, either positive or negative, since different diagrams can have different sign contributing to this sum. And then we need to square. So basically this will give us the full perturbation expansion in alpha electromagnetic. In QED, this value of alpha is rather small. It's 1/137. And therefore, the lowest order diagram would dominate. So for most purposes, it would be sufficient to neglect higher order diagrams. So we can forget about this one and try to compute only this diagram. And then we can calculate decay rate of cross sections using the previous formula, which we obtained for different cases. For decay, this one, for scattering the center of mass frame, this one, for scattering the lab frame, neglecting mass of the scattered particle, this one. Now let's consider a process where E plus E minus going to me plus me minus and work in the center of mass frame. And we will be considering the lowest order Feynman diagram. So here we can write down the matrix element following the Feynman rules, and we will note the incoming antiparticle V bar, incoming particle U, and we should remember that a joint spinor is always written first. So you have here V bar, and here you have U bar written first. In the center of mass frame, for such a scattering, we need to use this formula, where S would be just equal to P1 plus P2 squared, or 4E squared. In this case, also Q squared would be equal to S, and therefore the matrix element becomes simply this expression. Now I'm going really fast here just because we don't have time, but I really want to get to some qualitative discussion which comes at the end of the slides. So you will get the slides as well together with all the material. If you remember, previously we introduced the 4-vector current, which looks like this. And you can see that it has the very same form as the two terms in the square bracket in the matrix element here. So the same form as this element. Therefore, the matrix element can be written in terms of electron and muon current. So we have notation for electron current, for muon current like this, and we get the matrix element written like this. So when we remove these indices, we basically get the 4-vector scalar product for matrix element of two currents, electron current and the muon current. Looking at this, we immediately understand that matrix element should be Lorentz invariant in this form. Now, what is important in all this discussion is the spin. So in principle, when we consider the usual electron-positron colliders, circular colliders, electrons and positron beams would be not polarized, and therefore there should be equal number of positive and negative helicity states. There will be 4 possible combinations of spin in the initial state, like right, left, right, right, left, left, and left, right. And in the same way, there are 4 possible helicity combinations in the final state. So in total, 4 times 4, we get 16 combinations for possible scattering. In principle, to account for all these states, we would need to sum over all 16 possible helicity combinations like this, like all this matrix element, and then average over the number of the initial helicity states, which are 4. So we would need to evaluate the scalar product for all 16 helicity combinations. But fortunately, it's what we will discuss now, in the limit where energy of the particles is much larger than the mass of the muon, only 4 helicity combinations would give non-zero matrix elements. So this is an important feature of QED or QCD. We can see it directly by calculations. So for example, We can take again center of mass frame, take this limit, ultra-relativistic limit. And in this case, the moment of the incoming particles will be expressed through the energy, momenta outgoing particles would be expressed through the energy, and the scattering angle theta, which is the angle between negative muon and incoming electron. Now we need to remember from the lecture what is the left and right-handed helicity spinors for particles and antiparticles. So here we just use the expressions which we obtained in one of the lectures. And write them down, again, neglecting the masses. So we get the following expressions for the four spinors which we are interested in. Then the initial state electron can be in the left, here left or right-handed helicity state. And then the initial positron, we need to remember that it has theta equal to pi, therefore it can look like this. And then in the similar way, we can write down the spinors for final state muons with polar angle theta and choosing phi equal to 0. The same for the mu plus. And then what we want to do is to compute this scalar product. And for this, we can consider muon current for four possible helicity combinations, like this. Right, 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 left, left, right, and left, left. So what we want to do to evaluate this muon current for all helicity combinations. Basically, what we would need to do is to take the spinor, how it looks like, take the gamma matrices, how they look like, and do multiplication. So this multiplication in elements would look like this. You don't need to repeat it. And then, basically, we just take the explicit expression for the, for example, mu minus right and mu plus left, using the expression for the spinors which we wrote down previously, and try to do this computation. So here we'll obtain these four results. Basically, 4-vector muon current for the right-left combination would look like this. And then we can compute it for each combination. So right-left is this one, right-right and left-left will be 0, left-right again would be this one. So basically, what is important here, what needs to be retained, is that in the ultra-relativistic limit, only 2 helicity combinations will be non-zero. So this is an important feature of the QED, and it applies equally to QCD as well. In the weak interaction, only 1 helicity combination would remain non-zero. And the origin of this we will discuss a bit later. But basically, as the consequence, only 16 possible helicity combinations. Of the 16 possible helicity combinations, only 4 will give non-zero matrix elements. So these 4 are all drawn here. Either we have right electron and left positron going to right muon and left muon, mu plus, which is denoted as MRR, then such combination like here, like this one, and like this one. So previously we derived the muon currents for the allowed helicities. Now let's see how it looks for the electron currents. Again, we can write down the same mass as previously and obtain electron current either directly computing it from using by using the equation or from the expression from the muon current. So you can take the muon current as you compute it and see that if we take the Hermitian conjugate of this muon current, we'll obtain the expression which you would need for the electron current. Therefore, what we do, we take our result which we obtained for the muon current and get directly the answer for the electron current. Okay, it's extremely quick, but again, it's not, this mass is not something which I think needs to take a lot of attention in this discussion. So finally, what matters is that we can calculate this matrix element for all the 4 possible helicity combinations. As an example, we will do it for this one, which is denoted as MRR. So here, first subscript would refer to the helicity of the electron, and the second one to the helicity of the negative muon. We don't need to specify other helicities due to this helicity conservation, since only certain combinations would be non-zero. So by using our result previously, now we just need to do a scalar product of these two vectors, and we get this expression for MRR, that amplitude is proportional to 1 plus cosine theta and proportional to the alpha. In the graphical representation, it will look like this. So you see that MRR as the function of the scattering angle theta of the negative muon behaves in this way. And actually, this is very easy to understand from the picture of the spins, which you can see here. So look, the spin of this electron adding up the spin of this positron gives you total spin equal to unity. And then for the scattered muons, total spin is equal to unity in this direction. And then, of course, if muon flies to the to the angle pi in the opposite direction, the amplitude of such process, of course, should be equal to 0, because you will have the final spin going in the opposite direction to the initial spin. So this cannot happen. And this is what you can see in this picture. And maximal amplitude would be when the spin of muon system is aligned with the spin of the electron system. That's why the total amplitude behaves like this. The similar considerations go to the other three cases. Now, the cross-section is obtained by averaging, so 1/4, over the initial spin states and summing up over the final spin states. So summing up all the squares of the amplitudes. If we do the exercise, you will see that the differential cross-section of this process would be proportional to 1 plus cosine squared over theta. So it will look like this red line, which is the sum over all possible combinations. Now let's see how it actually talks with the experiment. So here for you, the graph from the actual experiment carried out in 1983 at the Mark II collider. And the energy of this collider, the square root of S, was equal to 29 GeV. So this energy is well below the Z boson mass, which is, as you know, is about 90 GeV. And in this graph, you can see the following thing. You can see the data points with uncertainties. And then you can see two theory curves. So first curve, dashed one, corresponds to the pure QED calculation as we did now, but to a bit higher order. So we computed to our result to the order of alpha squared. Here is to compute it to the order of alpha cubed. It becomes slightly asymmetric when you go to the higher order, but this asymmetry is not visible by eye here. So this dashed curve seems to be symmetric. And then solid curve takes into account also Z contribution. So the fact that this diagram can go not only via photon, but also via Z. And you can see that this solid curve describes the data much better. So basically, the energy much below the energy needed to produce a Z boson, you already are able to see the effect of the presence of a new theory beyond the one which you're looking at. So you're looking at QED, and you see that QED alone, quantum electrodynamics alone, does not describe the observed data. So even at lower energies, it's possible to see the contribution of basically heavier particle, which you cannot produce directly yet, but you see how it impacts the result. Then, so here we obtain the differential cross-section. We can also compute the total one. For this, we need to integrate our result over theta and phi. And from here, we can compute the total QED cross-section for this process, which is simply equal to 4 pi alpha squared divided by 3s. And again, you can see the plot where the measured cross-section of this process, plus e minus going to mu plus mu minus, is plotted as a function of square root of s. So black curve corresponds exactly to this computation at the lowest order, and points correspond to measurements at the various accelerators. So you can see that the lowest order cross-section calculations provides already a good description of the data, and This is an impressive result in the sense that from first principles, we have arrived at an expression for the electron-positron annihilation cross-section, which is good up to 1%. So you see, this is how theory is being tested with experiment and is being confirmed. Now, a small discussion about the spin consideration. So this angular dependence, which we obtained by just through direct calculations, can be understood in terms of angular momentum, what I already mentioned previously. So because of the allowed helicity states, the electron and positron interact in the spin state with the SZ projection, so with the spin component at the Z axis equal to plus minus 1. So we have total spin 1 state aligned along the Z axis, either plus 1 or minus 1. And similarly, muon and anti-muon also are produced in the total spin 1 state aligned along an axis with the polar angle theta. So in final matrix element is just equal to the product of these two-wave functions, where psi is the spin state of the final muon pair. Now we can evaluate this expression. For this, we need to express this in terms of eigenstates of the spin projection Z. So it will be combined of three components. So projection along the Z-axis, which is equal to -1, then to 0, and plus 1. If we do a product, for MRR, we have initial spin this. That's why we get amplitude proportional to 1 plus cosine theta squared. For MLR, we get the term which is proportional to 1 minus cosine theta squared, so this one, and so on. Also, you can know that the spin average matrix element derived above is written in terms of the muon angle in the center of mass frame. So this theta angle. This theta angle is not Lorentz invariant, of course, but the matrix element itself should be Lorentz invariant. We can express it in principle through the Lorentz invariant variables so that it will be valid in any reference frame, and for this, we can use the Mandelstam variables, so T, U, and S. So again, I skip the detailed derivation, it's just written here. You can see it in the slides later on. And one final notion which I would like to go over is the chirality. So far we talked only about the helicity eigenstates. And here we have again the expression of the helicity eigenstates in case of the ultra-relativistic limit or massless particle. Now, if you define the matrix gamma 5, which is the product of all four gamma matrices, we can see that at the same limit, these helicity eigenstates would be eigenstates also of gamma 5. In general, eigenstates of gamma 5 are defined as left and right-handed chiral states. You right, you left, you right, and you left. So this is a definition. And in this limit, in the ultra-relativistic limit, the chiral eigenstates would be identical with the helicity eigenstates. So this is a subtle but important point. So in general, helicity and chiral eigenstates are not the same, and only in the ultra-relativistic limit of massless particles that they become identical. Chirality is an important concept in the structure of QED and any interaction of this form. Why so? So you can see it if you define the projection operators. PR, which is equal to 1/2 1 plus gamma 5, P left, which is equal to 1/2 1 minus gamma 5. And these projection operators project out the chiral eigenstates. So right one projects out the right chiral eigenstate. When it acts on the left one, we get 0, and vice versa. And then we can write any spinor, psi, as the sum of the two left-handed and right-handed chiral components, always. So you just split it in two parts like this. In QED, the basic interaction between the fermion and the photon is written in this form. And again, if you decompose the spinors in terms of the left and right-handed chiral components, and use the properties of the gamma 5 matrix, we will show that we can show that these two elements, these two parts in this expression are equal to 0, and only a certain combination of chiral eigenstates contributes to the interaction. So this statement is always true. And this basically is also equivalent to the result which you obtained previously for the so-called helicity conservation. So again, just to go over the conclusions, in the ultra-relativistic limit, the chiral and helicity eigenstates are equivalent, and therefore for this limit, only certain helicity combinations contribute to the QED vertex. That's why previously we found that for 2 out of the 4 helicity combinations for the muon current were 0. So here you can see the nice plot, which basically shows which which helicity combinations are possible in the vertex. So you can see for scattering, basically we see the spin flow goes like this or like this, and these two diagrams are not allowed. They give 0 matrix element. And for annihilation, the spin combination looks like this. Summary of all this discussion, which I arrived very quickly at the end of this lecture, is that we obtained that in the center of mass frame, the differential cross-section for E plus E minus going to mu plus mu minus looks like this. Here we neglected masses of the muons and assumed that energy is much greater than the mass of the muon. In the QED, only certain combination of left and right-handed chiral states give non-zero matrix element, and chiral states are defined by the chiral projection operators, which look like this. Now, in the ultra-relativistic limit, the chiral eigenstates would correspond to the helicity eigenstates, and only certain helicity eigenstates will give non-zero matrix element. So this is the end of this slide. Again, I realized that this was extremely quick, but we didn't have much time left at the end of the lecture, and I really wanted to give you some conclusion over all the elements over which we went in the previous lecture. So you'll have the slides available. Also, I promised you that I will answer your questions and provide these answers in the slides as well. And if you have additional questions to the materials which we discussed in these slides, please don't hesitate to write me directly and to ask your question. And now I arrived at the end of the lecture in time, by sacrificing, of course, some level of clarity in the slides, in the discussion. So in this case, I stop the recording.